Hello everyone. In this lecture I will discuss phonons to thermal properties. In this lecture I will discuss two things: heat capacity of a phonon gas and the effect of the anharmonic lattice interactions on the phonons and on the crystal. So let's start with phonon heat capacity. When we discuss heat capacity, we actually mean about the heat capacity at constant volume, which is more fundamental than the heat capacity at constant pressure. The heat capacity at constant volume is defined as CV equal to partial U partial T at constant V. In such a way, U here is the energy, T here is the temperature. One more thing to consider here is the contribution of the phonons to the heat capacity of the crystal is called the lattice heat capacity, or C lattice, or the lattice heat capacity is the contribution of the phonons to the heat capacity. Another thing to define is the total energy of the phonons at a temperature tau here, let's know tau here, which is equivalent to kBT. In such a way, kB here is Boltzmann constant and T is the temperature. This total energy is defined as U lattice equal to double sum Kp U Kp, or double sum Kp and Kp h bar omega Kp. K here is the wave vector and P here is the polarization. Now Nkp, this one here, is the thermal equilibrium occupancy of phonons of wave vector K and polarization P. Now this form Nkp is given by Planck distribution function, which is equal to n, or 1 over exponential h bar omega over tau minus 1. The symbol, this one here, denotes as the average thermal equilibrium. This is average thermal equilibrium. Now let's define Planck distribution. Let's assume that we have a set of identical harmonic oscillators in thermal equilibrium. This way, the ratio of the number of oscillators in their n+1 quantum state of excitation to the number of the nth quantum state is defined as n here, n+1, the number of oscillators in their n+1 quantum state, to the n in this case here is the number of the nth quantum state. It's equal to exponential minus h bar omega over tau in such a way tau here is the kBT. Kb again, it's Boltzmann constant, and T is the temperature. And from this definition, the fraction of the total number of oscillators in the nth quantum state is defined as n here with respect to ns equal to exponential minus n h bar omega over tau divided by summation over all s from 0 to infinity, this one from 0 to infinity, exponential minus s h bar omega tau, and this is defined as the total number of oscillators. And therefore, the average excitation quantum number of the oscillators is defined as n, this one here, it's equal to summation over s, state s, here exponential minus s h bar omega over tau divided by summation over s states exponential minus s h bar omega over tau. Now let's use this series here. Summation x to the power s, it's equal to 1 over 1 minus x. If we and summation s x to the power s equal to x d by dx summation x to the power s, which equal to x divided by 1 minus x square. If we try to rematch this series with this one here, this series here with this one here, in such a way x here it's equal to exponential minus h bar omega over tau, and after all n here will be equal to x over 1 minus x, or equal to 1 divided by exponential h bar omega over tau minus 1. Now let's define normal mode enumeration. The energy of a collection of oscillators of frequency omega kp in thermal equilibrium is defined as U lattice, as we just defined, it's equal to double sum k wave vector polarization p and kp h bar omega kp, and n equal to 1 over exponential h bar omega over t minus 1. If we substitute this back in this one here, we will find that U, which is in this case the energy of a collection of oscillators, equal to double sum over k p h bar omega kp divided by exponential h bar omega kp over tau minus 1. It's more convenient to replace the summation over k by integration. In this case here, U will become equal to summation over all polarizations integration dw d p of omega h bar omega over exponential h bar omega over tau minus 1. If we assume that x equal to h bar omega over tau, or it's equal to h bar omega over kb t, then by finding partial u, partial t, we will find C lattice, and remember C lattice, it's equal to partial u, partial t at constant v. In this case, this is u, this one here. C lattice, it's equal to kb summation over p integration dw dp of w x square exponential to the power x divided by e to x minus 1 square. Now if we look to this C lattice formula, we will find that the main problem is to find this part of the integration. Once we find this part of the integration, we can calculate C lattice. Now d omega here is defined as the number of modes per unit frequency range. So it's called the number of modes per unit frequency range. Or in other words, it's called density of states. So the omega here is defined as density of states. Again, the main problem here is to find this density of states. Now, in order to understand this density of states, let's start with density of states in one dimension. Let's assume that we have a boundary value problem for vibrations of a one-dimensional line of length L, which has n plus 1 particles with A separations. Like this one here. If this is S equal to 0, the position for particle number 1, which is fixed in this case here, and this is 1, 2, until S equal to 10, which is fixed as well. So both ends of this one-dimensional line is fixed, S equal to 0, and the position S equal to 0, and at the position S equal to 10. The separation here, it's A, and the displacement is U, S in this case. The total length of this line is L. Now from this one here, each normal vibrational mode of polarization P has the form of standing wave. In such a way, US here is the displacement of particle S. Therefore, US here, it's equal to U0 exponential minus I omega kp t sine S k A. In such a way, omega here kp is related to k by appropriate dispersion relations. K in this case, it's equal to pi over L, 2 pi over L, 3 pi over L, and minus 1 over L pi. Now if we substitute K equal to pi over L, we will get US is proportional with sine S pi A over L, and this solution vanishes for S equals 0, and s equal to n. The meaning of vanishing displacement here, it means it's standing waves in the both ends. Again, we have here n minus 1 allowed independent value of k. Remember, we have 3 polarizations P for each value of K. So in one dimension, 2 of these are transverse and 1 is longitudinal. Now in 3 dimensions, the polarization are only for wave vectors in certain special crystal directions. In this case here, note 3 polarizations for each value of K. Now out of 3, 2 of them is transverse and 1 is longitudinal. So 2 here is 2 transverse and 1 longitudinal. Now let's consider the case for density of states in 2 dimensions. So if this is particle 1, 2, this is the displacement us, and here is the spacing a in this case. This is s equal to 0, s equal to 1, 2, until s equal to 8. Because of the symmetry, the allowed values for k are, this is 0, 2 pi over L, 4 pi over L, 6 pi over L, again minus 2 pi over L, minus 4 pi over L, and so on, and this is K. And therefore us here, it's equal to u naught exponential I ska minus omega k t. Note for periodic boundary conditions, the number of modes per unit range of k is L over 2 pi. For all k values here, this is k greater or equal to minus pi over a and less or equal to pi over a, or 0 otherwise. Again, we would like to find the density of states dW. In this case, the number of modes dW in the frequency range, the omega at omega is given in one dimension as d1 omega d omega equal to L over pi dk over d omega, which equal to L over pi d omega by d omega by dk. Now we will come to the main part. Here is calculating the density of states in 3 dimensions. Now if we apply the periodic boundary conditions over n cube primitive cells within the cube of sides L in such a way, k in this case determined by the condition exponential I kx x plus ky y plus kz z, which is equal to exponential I kx x plus L plus ky y plus L plus kz z plus L. In such a way, kx, ky, kz equal to 0 plus minus 2 pi over L plus minus 4 pi over L until n pi over L. And remember, there is only one allowed value of k per volume, 2 pi over L cube in k space. In other words, L over 2 pi cube, it's equal to V over 8 pi cube. And remember, this is the allowed value of k per volume. One more thing to define here is the total number of modes with wave vector less than k, which is found in terms of this equation here. N in this case is equal to L over 2 pi cube 4 pi k cube over 3. And again, this is the total number of modes with wave vector less than k. And from this one here, the density of states for each polarization is defined as this one here. It's dn by the omega, or vk square 2 pi square dk by the omega. Now let's define Debye model for density of states. In Debye approximation, the velocity of sound is taken as constant. In this way, omega here, it's equal to Vk. In such a way, V in this case is the velocity of sound, which is constant. It's sound velocity, which is constant. By using this dispersion relation, omega is equal to Vk, and substitute this back in this one here, and by finding dk by the omega, the density of states will become, in this case, this one here, d omega equal to V omega square over 2 pi square V cube. Assuming that we have n primitive cells in the specimen, the total number of acoustic phonon modes is n. Now, by using the definition of n here, it's equal to L over 2 pi cube times 4 pi over 3 k cube. Now, in this one here, remember, L cube is actually the volume. Now, n over v in this case, it's equal to 1 over 8 pi cube times 4 pi k cube over 3. And if we eliminate this with this and this with this, you will get n over v, it's equal to 1 over 6 pi square k cube. Now remember, omega, the dispersion relation, it's equal to Vk. Now the cutoff frequency, let's name it d here, it's equal to Vk. Now k in this case, it's equal to omega d over v, and you substitute this back in this one here, you will find omega d cube, it's equal to 6 pi square v cube and over v, and this is called cut-off frequency. And from this cut-off frequency, we can find cut-off wave vector kd, which is equal to omega d over v, and which is equal to 6 pi square and over v to the power 1 over 3, and this is called cut-off wave vector. Now, the reason we are calculating this cut-off wave vector and cut-off frequency, in this case, in Debye model, we don't allow modes of the wave vector to be larger than this cut-off wave vector. So, the number of modes with k less or equal to cut-off wave vector is actually exhausting the number of degrees of freedom. In this case, the thermal energy U, it's equal to integration d omega, this one here, and omega h bar omega. In other words, it's equal to 0 to omega d, this one here, d omega v omega square divided by 2 pi square v cube times h bar omega exponential h bar omega over tau minus 1. And this one here for each polarization type. Now, for simplicity, let's assume that the phonon velocity is independent of the polarization. Therefore, U will here equal to 3v h bar over 2 pi square v cube integration 0 omega d omega cube divided by e to h bar omega over tau minus 1, which is actually equal to 3v kb to the power 4 t to the power 4 over 2 pi square v cube h cube integration from 0 to omega d xd, I'll mention xd in a moment, dx x cube e to x minus 1, where x here is equal to h bar omega over tau or equal to h bar omega over kb t, and xd equal to h bar omega d over kb t, or in other words, it's theta over t, and theta here is Debye temperature, which is defined in terms of omega d. So theta here will be equal to h bar v over kb times 6 pi square and over v 1 over 3. Now let's pull everything together and find u in this case will be equal to 9n kbt times t over theta cube integration from 0 to xd dx x cube over ax minus 1. Back to the definition of the energy here, this part here. It's easy actually to differentiate this part here to find the CV. Now CV, by differentiating this part, this one here, will be equal to 3V h bar square 2 pi square V cube kb t square integration 0 to omega d omega to the power 4 exponential h bar omega over tau divided by e to h bar omega over tau minus 1 square. In other words, CV here it's equal to 9 n kb t over theta cube integration 0 to xd dx x to the power 4 e to x minus 1 square. Now let's find the heat capacity at very low temperature. In this case, dBi at T cube low. Back to the equation, this one here. This one here. I'll just move it down. At very low temperature, the upper limit of the integral will become infinity. So in this case, xd will go to infinity. In this case, the integral will become integration from 0 to infinity dx x cube over e to x minus 1, and this will be equal to integration from 0 to infinity dx x cube summation from s equal to 1 to infinity exponential minus sx or equal to 6 summation from s equal to 1 to infinity 1 over s to the power 4. In other words, it's equal to pi to the power 4 over 15. Just to mention that the summation 1 over s to the power 4, we can find the value for this summation in standard tables. Therefore, u, after we just find the integral here, will become equal to 3 pi to the power 4 and kb t to the power 4 over 5 theta cube. Now, by deriving u with respect to temperature, in this case, CV here will be equal to partial u partial t, or in other words, approximately equal to 12 pi to the power 4 over 5 nkb t over theta to the power 3, or in other words, approximately it's equal to 234 nkb t over theta cube. Now, another model for calculating the density of states is Einstein model. In Einstein model, let's consider that we have n oscillators of the same frequency, omega naught, and in one dimension. So the Einstein density of states is defined as this one here, n delta omega minus omega naught, and delta here is the delta function centered at omega naught. So this one here is the delta function centered at omega naught. Therefore, u in this case will be equal to n h bar omega, or n h bar omega divided by exponential h bar omega over tau minus 1. We just wrote omega here in place of omega naught for simplicity. Now, once we calculated U, we can calculate heat capacity. So CV in this case, it's partial U, partial T at constant V, and equal to NKB H bar omega over tau square e to h bar omega over tau divided by e to h bar omega over tau minus 1 square. And this is actually the heat capacity using the Einstein model. Now it's more convenient to find the general expression for d omega. Now let's find that the number of states per unit frequency range is given by the phonon dispersion relation omega k, this one here, and the number of allowed values of k for which the phonon frequency ranges between omega and omega plus d omega is defined as d omega, this one here, equal to L over 2 pi cube over shell d3k. And remember, this one here is the number of allowed values of k for which the phonon frequency is between omega and omega plus d omega. Now, the big issue here is to evaluate the volume of this shell. So let's assume that ds omega expresses the element of area. Now, from this one here, d3k over this shell is actually equal to ds omega dk perpendicular in such a way ds here is the element of area, this one here, and the gradient of omega here dk perpendicular, it's equal to d omega. Therefore, ds omega dk perpendicular in this case, it's actually equal to ds omega d omega by the gradient of omega or ds omega d omega. And remember, gradient of omega, it's actually group velocity, just a quick reminder, equal to d omega by dk. From the above definitions, d omega, this one here, the density of states, it's equal to L over 2 pi cube integration ds omega over group velocity d omega. And if we divide both sides by the omega and write v here equal to L omega, and if we divide both sides by the omega, in this case here the density of states will be equal to v over 2 pi cube integration ds omega over group velocity. Now let's move to the second part of this chapter here, is anharmonic crystal interactions. In harmonic theory, the potential energy is limited in terms of quadratic and interatomic displacement. Now we have some consequences of using this harmonic theory, as two lattice waves do not interact and the single wave does not decay or change. As another consequence here of using the harmonic theory, no thermal expansions, and diabatic and isothermal elastic constants are equal. The elastic constants are independent of pressure and temperature, and the heat capacity becomes constant at high temperature. T is greater than theta. Just to mention that in real crystals, none of these consequences is satisfied exactly, and this can be explained because neglecting the anharmonic terms in the interatomic displacements. Now let's start with thermal expansion. The potential energy of the atom at a displacement x from their equilibrium separation at absolute zero can be written as u of x. Here it's equal to cx squared minus gx cubed minus fx to the power 4. In such a way, C, G, and F all positives. C, G, F all are positive. And x cubed here represents the asymmetry of the mutual repulsion of the atoms. And the term here, x to the power 4, represents the softening of the vibration at large amplitudes. So this one here represents the asymmetry of mutual repulsion, and this one here is the softening of the vibration at large amplitude. Now let's calculate the average displacement by using Boltzmann distribution function. In this case here, x equal to integration minus infinity to infinity dx x exponential minus beta ux divided by integration minus infinity to infinity dx exponential minus beta ux. Just for simplicity, we use just beta here equal to 1 over kBt. In such a way, anharmonic terms in the energy are very small comparing to kBt. In this case, let's expand the integral dx x exponential minus beta u and become here integration dx exponential minus beta Cx square times x plus beta g x to the power 4 plus beta f x to the power 5, or in other words, it's equal to 3 pi to the power half divided by 4 g over c to the power 5 over 2 beta to the power minus 3 over 2, and again the integration dx exponential, this is the dominant part, minus beta u, it's equal to, actually it's approximated, integration dx exponential minus beta cx square, or equal to pi over beta c all to the power half. Now it will become 3g over 4c square kb T. Now let's define thermal conductivity. The thermal conductivity coefficient K is defined with respect to the steady state flow of heat with a temperature gradient dt by dx. Now let's define here the flux of the thermal energy. J U is defined as minus K dt by dx. Now J here is the flux of the thermal energy, or energy transmitted across unit area per unit time. Based on this definition, the thermal energy transfer is a random process. Now the energy does not simply enter one end of the specimen and proceed ballistically in a straight path to the other end. Actually, it diffuses through the specimen. With the aid of the kinetic theory of gases, now K here equal to 1 over 3 C V L. C is the heat capacity per unit volume, and V is the average particle velocity. L is the mean free path of the particle between collisions. So C here, heat capacity, V here is the average particle velocity, L is the mean free path. If C is the heat capacity of the particle, therefore moving from one region at local temperature T plus delta T to another region at local temperature T, a particle will give up energy equal to, in this case, C delta T. Now, based on this, delta T between the ends of the free path of the particle will be given by delta T equal to dt by dx, Lx here, which equal to dt by dx Vx tau, and tau here is the average time between collisions. Therefore, the net flux of energy Ju. Here it's equal to minus n the x square c tau dt by dx, or equal to minus 1 over 3 n b square c tau dt by dx. Now for phonons, v is actually a constant. In this case here, the flux equal to minus 1 over 3 c vl dt by dx, with L equal to V tau, C equal to N C, then K equal to 1 over 3 C V L, and K in this case is the thermal conductivity. That's it. Thank you for watching.